Okay, welcome back, gentlemen. Hope you enjoyed your break. Time to get back to work now, and we are going to continue with stoichiometry. So hopefully you have some understanding of stoichiometry from last week. The key to that big stoichiometry worksheet is up there, and the work through video for several of the problems are up there too if you have any questions about that. But basically, we'll be doing more of the very similar thing, just a slightly more complex wrinkle into stoichiometry. And that is for limiting reagent and eventually percentage yield. Today we're just going to talk about limiting reagent and a few definitions and how to do the most simple types of these problems. So up till now, in all your previous questions, you've been given the amounts of one chemical. Let's say if I had 10 grams of hydrogen, how much water could I make? And you'd figure it out based on 10 grams of hydrogen. We never really talked about it, but you were assuming you had infinite amounts of oxygen. And that's not really true. In reactions, we actually are limited by the amount of every ingredient. So uh, basically, what happens in any given reaction is one of the reactants, one of the starting products, runs out, and that limits the amount of product you can make. And that is called the limiting reagent. Reagent is just another word for chemical. So the limiting reagent is the reagent in the reaction that gets used up and stops the reaction. So a couple terms. Uh, Again, limiting an excess reagent. Limiting reagent is just what's used up, what gets used up, and then stops the reaction, because once you're out of it, you can't make any more product. So the limiting reagent determines how much product you make. Any reagent that is not used up, in other words, there's extra of it left, is an excess reagent. So again, if you have a little bit of one ingredient and a lot of another ingredient, you'll have some of that second ingredient left over. And I will give you an example. So if I were making peanut butter and jelly sandwiches, if I were making peanut butter and jelly sandwiches, I had what you see in front of you, I had this amount of each ingredient. I had 4 pounds of peanut butter, 6 slices of bread, and 2.63 pounds of strawberry jelly. And these are real amounts and real things I actually have in my house, although I do have more than 6 slices of bread right now. So you have 4 pounds of peanut butter uh, and about over 2.5 pounds of jelly, but only 6 slices of bread. Well, how many sandwiches can you make? Well, you have enough peanut butter and jelly to make a ton of sandwiches, probably in the dozens of sandwiches. However, you only have 6 slices of bread. This 6 slices of bread, that number is going to limit how many sandwiches you can make. So you're limited to 3 sandwiches. Oh man. So you're limited to 3 sandwiches. Sorry, I was botching my spelling as I was writing it out for some reason. But you're limited to 3 sandwiches. You will have used up all the bread at that point. So the bread all gets used up. But you will have plenty of extra peanut butter and extra jelly. So in this case, in this kind of metaphor for a chemical reaction, our limiting reagent, the thing that limits us, will be the bread. It prevents us from making more sandwiches. It gets used up, prevents us from making more sandwiches. The 4 pounds of peanut butter will have a lot of extra peanut butter, and 2.63 pounds of jelly will have a lot of extra jelly. They would be excess reagents because we have extra of them. We've made all the product we can, which is peanut butter and jelly sandwiches, the 3 peanut butter and jelly sandwiches. But we've run out of bread, so we can't make any more. We still have lots of peanut butter, lots of jelly. They're in excess. That's what we say. When you hear the term in excess, if you see that near your problems or hear it said, that just means you have plenty of it, lots of extra. So actually, for all the problems you've seen so far, the stoichiometry problems that just give you one amount, it assumes all the other reagents are in excess. In other words, you have enough to make as much as you need uh, for whatever, and whatever amount you're given, that's the limiting reagent. So in real life, we have set amounts of each ingredient. We don't have an infinite amount of any ingredient. So if we look back to here, here's a real life example. So copper reacts with sulfur, excuse me, to form copper 1 sulfide. according to the following balanced equation, which is 2 copper and a sulfur make copper 1 sulfide. Uh, what is the limiting reagent when 80 grams of copper reacts with 25 grams of sulfur? So up till this point, we would just say how much copper sulfide can you make with 80 grams of copper? And that would assume you had all the sulfur you need, like an infinite amount of sulfur, but in fact that doesn't actually exist. When we do reactions, we have a finite amount of both product and reactant, and one of them will limit the reaction. So to find the limiting reagent, instead of just one stoichiometry problem, and you're going to love this, you get to do 2. So it's a whole bonus stoichiometry problem. So I know you're very excited about this. So looking at the problem like this, and I have it written out here, basically you're doing 2 stoichiometry problems, one with each amount, and you're going to find out how much product it can make. So the first one, you're going to convert the 80 grams of copper into grams of copper 1 sulfide. And the second stoichiometry problem you're going to do is the 25 grams of sulfur. You can convert that into grams of copper 1 sulfide. So I'm going to set these 2 problems up. These are regular stoichiometry problems, and then we'll talk about our results. Okay, so I've set up 2 stoichiometry problems. One starting with the 80 grams of copper and converting it to grams of copper 1 sulfide, and one starting with 25 grams of sulfur and converting it to copper 1 sulfide. This is just like the stoichiometry problems we did last week, or well, 2 weeks ago, last school week. I just take the 80 grams for the first one, convert it to moles by dividing by the molar mass, and then I change chemicals. And to change chemicals, I use the coefficients from the balanced equation. This is another one. You have to start with balanced equations for all stoichiometry. The simple stuff we did before and the more complex stuff we're going to, you need a balanced equation. So here it's 1 mole of copper 1 sulfide because there's nothing in front of copper 1 sulfide, which indicates a 1, and 2 moles of copper because there's a 2 in front of copper. And then I converted that to grams of copper 1 sulfide. 159.16 is just the molar mass of Cu2S. So 2 coppers and a sulfur equals 159.16. And I found that with 80 grams of copper, I have enough copper to make 100.2, which I rounded for sig figs down to 100 grams of copper 1 sulfide. So 80 grams of copper can make 100 grams of copper 1 sulfide. I did the same thing with sulfur. I started with 25 grams of sulfur and converted to copper 1 sulfide. One difference to be careful of, the molar ratios are different because sulfur, instead of a 2, just has a 1 in front of it. So it's a 1-to-1 molar ratio. So just be careful with the balanced equation there. And I find out I have enough sulfur to make 124.1 grams of copper 1 sulfide. Again, rounding for molar masses, that goes to 120. So what does this mean? Well, it means I can only make the smaller amount. This is what I will actually make. The reason for that is when I make 100 grams of copper 1 sulfide, I then run out of copper. That uses up all my copper. Yes, I have more sulfur left over, but that doesn't matter. The reaction stops because there's no more copper to react with it. So the lower amount when you do this tells you the amount you actually made. And the reagent or the chemical that gives you that amount is your limiting reagent. So this would be your limiting reagent. And then, of course, any chemical that is left over, in this case, it's just the other reactant. Any chemical that you have extra of, I should say, is an excess reagent. Notice that when we ask for limiting an excess reagent, it's the chemicals we start with. That 100.2 grams of copper 1 sulfide, that's what's made, but that's not your limiting reagent. That's what's actually made. And there is a technical term for it. The amount you actually make is called your theoretical yield. So the theoretical yield, it's theoretical because we didn't do the reaction. We just did a bunch of math to indicate how much we should make. So it's theoretical. If we actually ran the reaction in a lab and got an amount, that would be the actual yield as opposed to the theoretical yield. And we'll talk about those more on Wednesday when we do the next part of this. So you start with 2 amounts, an amount of copper and an amount of sulfur, and one of them runs out and limits the amount of product you can make. In this case, the copper runs out first, and that limits how much copper 1 sulfide can be made. So copper is the limiting reagent, and you make 100 grams of copper 1 sulfide. The excess reagent is sulfur. You have enough sulfur to make 124 grams, which means some amount of sulfur will be left over. We aren't going to talk about how much excess reagent is left over yet. We're just going to say there's extra of it, and that's where we're going to stop for this lesson. So I'm going to do a couple more examples, and that'll be it. So you should know what a limiting reagent is, what an excess reagent is, and know how to find those out given the amounts of two reactants. And then you should know what a theoretical yield is. It's just the lower amount you make when you do the stoichiometry. So you're in two stoichiometry problems. The lower product amount is the amount you make. In this case, 100 grams of copper 1 sulfide. So here's my first of the two examples I'm going to do. If you start a reaction with 12 grams of hydrogen gas and 64 grams of nitrogen gas, which will be the limiting reagent, and how much ammonia gas will you make? So you need to start with a balanced equation here. This is clearly going to be a synthesis. We're starting with two elements by themselves, and it tells you in the equation, in the problem, what's going to combine into. We've seen this one a lot. Hydrogen and nitrogen make ammonia. This is the Haber process. The guy who, won a Nobel Peace Prize, but also kind of invented chemical warfare. Kind of a mixed bag with him. So N2 plus H2 gives us NH3. And technically, it did tell us these are all gases, so you can put in the parenthetical subscripted G for gas. So we should balance it. And this one's easy to balance, and you've seen this a whole bunch of times. I'm actually going to start with the hydrogen in this case, because the nitrogen is easy, and I can see I have an odd-even problem with the hydrogen. I have an H2 here and an H3 over here. So I'm going to have to make it equal something that is a factor of both 2 and 3. So that's going to be 6 in this case. You want to go with the lowest one. So I'm going to need 3 hydrogens, and it's going to make 2 of those, and that also balances out my nitrogens. So on each side, I have 2 nitrogens and 6 hydrogens. So that's the balanced equation. That's what you start with. So I have 2 amounts of products, or 2 amounts of reactants, excuse me. The 12 grams of hydrogen and the 64 grams of nitrogen. So what I'm going to do is start 2 stoichiometry problems. One going from 12 grams of hydrogen to grams of NH3. That should be an H2 there, excuse me. And one with 64 grams nitrogen going to grams of NH3. Another thing to be careful of, these are both the Brinkelhoff, the diatomic molecules, so it's N2 and H2. Make sure to remember those. We learned them all. You're told to memorize them. You got 7 points if you did. Almost all of you got the 7 points. So just remember, if it's one of those Brinkelhoff or diatomic molecules, when we say hydrogen, by default, we mean H2. If we say nitrogen, we mean N2. So I'm going to set these stoichiometry problems back and solve them, and then come back and discuss what they mean. Okay, so I've set up the 2 basic stoichiometry problems, one starting with those 12 grams of hydrogen and going to grams of ammonia, and one with 64 grams of nitrogen gas and going to grams of ammonia. Again, be careful with the molar ratios, those numbers in the middle when we change chemicals. That comes from the balanced equation. So ammonia gets a 2 in both equations because I had a 2 in front of it. Hydrogen gets a 3, and nitrogen gets a 1. Be careful with those, just because you don't want to get the problem wrong from a simple mistake like that. Everything else is pretty straightforward stoichiometry, and we find with 12 grams of hydrogen, we can make 68 grams of nitrogen, or of ammonia, excuse me, 68 grams of ammonia. And with 64 grams of nitrogen, we can make 78 grams of ammonia. So what's going to happen is we're only going to make the 68 grams. Because at that point, we run out of hydrogen. So this is what we actually make. And that would be the theoretical yield. Because once we make 68 grams of ammonia, we've run out of hydrogen. Yes, there's extra nitrogen, but it doesn't have anything else to react with. So that means that the hydrogen, the one that runs out, that is your limiting reagent. And the nitrogen, of which there is extra, is your excess reagent. Again, note, limiting and excess reagent refers to the things you start with, the reactants, and theoretical yield is the amount that you make, the lower of the two amounts, because we can't actually make 77.8 grams of ammonia, or 78 grams of ammonia. We do not have enough hydrogen for that. So this cannot actually happen. It can't happen because we run out of hydrogen before we get there. Even though we have enough nitrogen, we don't have enough hydrogen, so you have to stop. Okay, I'm going to do one more example, and that'll be it for this video. And again, we'll do another video on Wednesday where we talk about how we figure out exactly how much excess reagent we have left. So we kind of figure out that third piece of the puzzle. So what would be the limiting reagent if 82.4 grams of C3H6 were reacted with 273 grams of O2? So this one, you have to start with your basic stoichiometry, which means figuring out what type of reaction it is and balancing the equation. Well, it's C3H6 plus O2. And that's going to give us something. And you guys should be able to recognize this as combustion of a hydrocarbon. This C3H6, that's a hydrocarbon, and it's definitely being combusted, react with oxygen. And whenever you have combustion of a hydrocarbon, it means you're going to make CO2 plus H2O. So that is our skeleton equation, and now we have to balance it. And I'm not going to go through all the balancing steps because that's kind of a pain. I'm just going to balance it and come back. So I'll come back with the balance. Okay, so I've balanced the equation. You end up with two C3H6s, which are propene. Technically, you wouldn't have to know that name. Plus 9 oxygen gases gives you 6 carbon dioxides and 6 waters. So that's your balanced equation. And if you don't have that right, because you need those coefficients for the stoichiometry, it means pretty much everything else afterwards is going to be wrong. So make sure you start with a proper balanced equation. So you should be able to recognize this as combustion, know that combustion of a hydrocarbon makes carbon dioxide and water, and then balance it. So I'm going to, again, do 2 stoichiometry problems because we're given 2 amounts. I'll do one starting with, 84.2 grams of the propene, or 82.4, number dyslexia, C3H6. And now, I have more than one product, so this is a little bit more complex. So do I find out how much CO2 I made or how much H2O? Well, it actually doesn't matter. Whichever one is the limiting reagent for carbon dioxide is also going to be the limiting reagent for water. So if it's just asking you what's the limiting reagent, you can choose which product to go to, as long as you do the same one for both. You can't take one of the stoichiometry things to CO2 and one of them to water and make a comparison. That doesn't make any sense. However, I would strongly suggest that you read ahead in the problem, because if I just read the next sentence, how much carbon dioxide would be produced, well, I can save myself a step if I just take these to carbon dioxide. If I took them both to water, if I did these both to water, I would then have to go back and do another stoichiometry problem to figure out how much carbon dioxide I have. So I'm just going to go straight to carbon dioxide. So this 2 grams of CO2. And then again, looking at my second number, 237 grams of oxygen, 2 grams of CO2. So I'm going to set up those 2 stoichiometry problems and do the math. And again, we'll talk about what the answers are. Okay, so I've set up and solved the 2 stoichiometry problems, and we see that 82.4 grams, of the C3H6, the propene, will get us 259 grams of CO2 if all of it can react. And the 237 grams of oxygen will only get us 217.3 grams of CO2. I rounded both those to 217 and 259. I rounded both those to sig figs. So the amount we actually make, or our theoretical yield, will be the lower number. This is the theoretical yield. So that's how much you would actually make. So that would answer this, 217. And which one is the limiting reagent? Well, the one that's the limiting reagent is the one that made the theoretical yield, the one that runs out. Once you get to 217 grams of CO2 made, you run out of oxygen. And even though you have extra C3H6, it can't do anything. So this is your limiting reagent. And then this would be your excess reagent. So one thing to notice, for a lot of them, it just seems like you take the bigger number, you go, okay, that's going to be excess. I have more of it. And sometimes that works and sometimes it doesn't, but you can never count on it. Here, we had only 82 grams of propene, but we had 237 grams of oxygen. It didn't matter because of the way the moles worked out, because of that molar ratio, and also because of the molar masses of all the reactants and products. What we ended up doing is 237 grams of oxygen, even though it's a lot of oxygen compared to the amount of propene we had, still makes less CO2. It makes less of it, and that's what matters. So it will run out first. And so that's our limiting reagent. And again, we would make 217 grams of CO2. So that's limiting, excess reagent, and theoretical yield. So that's what happens when you get a real world situation. Instead of just being given one number, like just given 82 grams of propene, you're actually given both reactants, which is what happens in real life. You don't have an infinite amount of one reactant. You are limited by both reactants. They have finite amounts. So to find out which one will run out first, and that's the one that limits your amount that you can make. So one last thing, I have included on the classroom page with the worksheet and with this video, this second part of a how to do stoichiometry kind of page. Just tells you step by step how to do limiting reagent problems. Just so you know, up till now, we have gotten through step 3. Step 4 and 5 we'll talk about on Wednesday. But you might want to look at this and kind of follow it along as I go through the examples or, as you're doing your problems. For the regular stoichiometry I did in these, you just use that how to do stoichiometry worksheet. That's those same steps. Now we're just doing 2 of those. This just gives you the details to how to set that up. So this will be there too for you, the how-to sheet. Other than that, feel free to ask any questions, but work on the worksheet. For the worksheet, only do the red problems. So the problems are in red or green. The red problems are the problems that we've covered. The green problems go on to stuff we haven't covered. So we'll do that Wednesday, and by the end of the week, the worksheet due Friday, you'll have everything done, or at least I will have taught you everything, and hopefully you will go and then do everything. Okay, so have a good day. Welcome back to school. I know you're very excited to be here. And now you get to do 2 stoichiometry problems per question. So what could be better than that? Have a good day, gentlemen.